Now we look at another theorem that is very similar to one we looked at in the previous chapter regarding sequences. Theorem 2.6 says that if you've got two functions, f and g, whose domain is capital D, both cases, and they go into R, and you got x naught as an accumulation point of D, then the following is true. If the function f is bounded in a neighborhood of x naught, and the limit as x goes to x naught of g of x is 0, then you might be able to guess what the conclusion of this would be. Then the limit of f times g of x as x goes to x naught is 0. Now, I like the way this theorem is worded. In a few cases up to this point, I've said that I thought the statement of the theorem could have been made a little bit stronger. I was almost expecting the theorem in the textbook to say, okay, we've got this set up. It's going to say if x is bounded, period, not just in a neighborhood of x naught. It would certainly be true if f were bounded, because it would be bounded everywhere, so it would be bounded in a neighborhood of x naught. But this is much more precise. I like the statement of this theorem much better. Well, let's take a look at the proof. All right, well, all of this stuff is true, is assumed to be true. After the then is what we need to prove. So I need to prove that a limit of a function as x goes to x naught is equal to 0. So I'm going to need an epsilon greater than 0 to start off with. Let epsilon be greater than 0, or you can say let epsilon greater than 0 be given. The next thing I'm going to look at is this part. What does that tell me? It's bounded in a neighborhood of x naught. Therefore, I can say, let's see, I'm going to use delta 1 and m, two numbers that are both greater than 0. And you might guess what's going to happen. I'm going to have this function be bounded by m. And in what neighborhood? The neighborhood is going to be x naught plus or minus delta 1. So, the definition of being bounded means that f of x in absolute value is less than some number. And I'll say for all x in, let's see, how do I want to do this? For all x in the interval of x naught minus delta 1 to x naught plus delta 1. All right, this statement exists. This statement is true because of what is underlined right here. F is bounded in a neighborhood of x. So let me repeat that one more time. Here's the neighborhood of x. And for all x in that neighborhood, f of x is less than m because it's bounded. I know these two numbers exist because f is bounded. And let me just, as I've done before, write this part in a different way. I could have said for all x such that x minus x naught is less than delta 1. So this thing right here is the same as this. All right, well, as you might suspect, if you happen to remember the corresponding proof we did for sequences, I'm going to say for epsilon prime equal to epsilon over m, this is a positive number because epsilon and capital M are both positive. Let delta 2 greater than 0 be such that, and now I am, let's see, oh yeah, now I'm using this part. I thought this was the conclusion. Here's the conclusion. Now I'm going to use this part right here. The limit as x goes to x naught of g of x is equal to 0. Therefore, for this positive number epsilon prime, I know there is a delta 2 such that if x is in the domain and it's a limit, so I need to say x less than x minus x naught less than delta 2. So this means that x is within delta 2 of x naught, but it's not equal to x naught. If that's true, we get that the g of x minus 0, I'm just going to write that as g of x, get rid of the minus 0, is less than delta prime. Okay, so again, why am I able to make that statement for this positive number? Why do I know there's such a delta 2 here? Because this. I just simply use the definition of what it means for the limit of the function g of x as x goes to x naught being 0. Well, let's, I need to find a delta, so I'm going to take my delta to be the minimum of the delta 1 that we talked about and the delta 2 that we talked about. Therefore, this would be true because as long as x is within delta of x naught, and if this is true, that's true. And this would also be true, which means this would be true as well. Okay, so I've got my delta, and maybe y'all can just continue this by saying, and let x be in this set. So this is kind of my hypothesis. This just says x can be any number within delta of x naught, and as long as it's in the domain. I can finish it up with one more sentence. Therefore, we get f g of x minus 0, which I'm going to rewrite as f of x g of x in absolute values, which is equal to f of x in absolute values, g of x in absolute values, just by the properties of absolute values. Now we can get to where we want to get. We want that to be less than epsilon. But since x is within delta, which means within delta and within delta 1 and delta 2 of x naught, f of x is less than m. F was the bounded function. And g of x is less than epsilon prime. And that happens to be m times epsilon over m, which just gives us epsilon. And that's the end of the proof.